Okay, it is a great pleasure to introduce James Maynard, professor at Oxford University. He has made a number of breakthroughs in the theory of prime numbers, in particular ideas leading to the best known results for pairs of primes exceptionally close together, as well as being able to produce clusters with arbitrarily large number of primes exceedingly close together. And as well been involved in the resolution of a long-standing conjecture by Erdős on large gaps between primes. His awards include the Ramanujan Prize, the Whitehead Prize, and the EMS Prize. He will now tell us about primes in arithmetic progressions and sieves, please.
OK, thank you very much for the introduction, and thanks a lot to the organizers for inviting me to speak here. It's a great honor to be here for Enrico Bombieri, who's certainly one of my sort of mathematical heroes. I guess you've already heard many stories about Bombieri's mathematical accomplishments, but one story that I thought I'd like to share with everyone is that my parents aren't mathematicians at all. They were both linguists, but as I got into mathematics and became more interested in mathematics, they sort of started to read up a little bit about the world of mathematics as an outsider, but they always found it slightly difficult to appreciate sort of who these mathematicians were and what the importance of any of these theorems were, so they maybe never fully appreciated things, apart from one story that made a very big impression on them, was this story about Enrico Bombieri sending a joke email for April Fools, claiming that a young physicist had proven the Riemann hypothesis that then went somewhat viral at the time. And so this story always somehow stood out, and so they very much remember Bombieri's name, and they always refer to him to me as the fun one. So I'm sure my parents are very pleased that you've won the prize as the fun one. OK, so I would like to talk about primes in arithmetic progressions and sieves. Just as a general thing, this is intended to be a colloquium-style talk, so I'm hoping that this is accessible, but please do ask questions if things aren't clear. And I'd like to not try and be at all comprehensive in terms of talking about Enrico Bombieri's work, but maybe just focus on a couple of his favorite results and how they fit into my research and how they relate to me. So it's a slightly personal take on some of Enrico's work is what I'd like to focus on today. But maybe I'll start off with the Riemann hypothesis. So we've already seen this a little bit in Enrico's talk. So this is normally stated as the non-trivial zeros of the Riemann zeta function all lie on this special line with real part equal to 1/2, but maybe a slightly more low-level way of stating the Riemann hypothesis is just as a inequality where here, what I've written as pi of x is just the number of primes which are less than or equal to x. So this is a completely equivalent form of the Riemann hypothesis, and there's this complicated object which, as an analytic number theorist, we are very interested in understanding the number of primes up to x. And what this says is that the number of primes up to x is very well approximated by some simple, smooth analytic function, which we should think of as being this integral is easy. So maybe this is interesting but complicated. This is kind of easy and well understood. But obviously, this is a step function that jumps by 1 whenever x gets to a prime number, so it's certainly not equal to some nice, easy, smooth analytic function. So it's only equal to this up to some error. And the Riemann hypothesis is stating that the error in this approximation is very small. So when x is very large, this approximation will have size about x over log x, and this error term will have size slightly bigger than the square root of x, and so will be of size roughly the square root of the main term. And so this is going to have maybe half the digits of the main term approximation, so this is really somehow a very good approximation. The constant 100 here is completely unimportant, it's just some constant, although there's a lot of structure going on here, and so there's this sort of fun fact that there's a self-improving constant. So if you prove this with a constant 1000, you can also then replace it with a constant 100, and in fact you can replace 100 with some smaller constant that depends on the zeros. Okay, so this is the Riemann hypothesis. You get $1 million if you solve it. It's often dubbed the most important open problem in mathematics, but often for lots of consequences for prime numbers, it turns out that a slight generalization of the Riemann hypothesis is the sort of really key thing for further applications. And so maybe I'll call this RH, and then GRH will be the generalized Riemann hypothesis. And again, this can be formulated as zeros of certain L functions all lining up on special lines, but maybe a more down-to-earth way of writing this is that the number of is a counting estimate for the number of primes in arithmetic progressions, having a very good approximation again. So I'm hopefully writing it in a way that will look somewhat similar to the phrasing of the Riemann hypothesis, where here this is not just counting the number of primes up to x, but the number of primes up to x which are congruent to A modulo Q. And okay, this is obviously going to be false if A and Q have a common factor. So this is for x being bigger than or equal to 2, and A and Q being two coprime integers. And so again, this is saying that if you're interested in the number of primes up to x in any given residue class, this has a very simple main term approximation, and then some small error term. And this is just a reformulation of this question about the zeros of certain L functions. And I guess maybe one comment on that front is I'll just highlight this exponent 1/2 here as being very much related to the line with real part 1/2. If you could prove a weak version of the Riemann hypothesis that all the zeros of the Riemann zeta function had real part at most 3/4, then you get a statement very much along these lines, but with 1/2 replaced by 3/4 as a bound. And so it would be a weaker statement, but it would still be an amazing breakthrough. Phi here, yeah, sorry, this is the number of possible coprime residue classes. So this is the Euler phi function. So this is saying this main term approximation doesn't depend on the residue class A, apart from the restriction that A is coprime to Q, and so this is saying that every one of those different residue classes gets roughly the same number of primes. Maybe we could turn off the... Oh, great, thanks. Okay. Unfortunately, we don't know how to solve the Riemann hypothesis, and we don't know how to solve the generalized Riemann hypothesis, and this is a fairly major barrier to making progress, and we can't even get one of these weak results where we replace 1/2 by some other constant like 3/4. And maybe well, certainly one key issue is we can't rule out so-called Siegel zeros, which are zeros of L functions very close to the point 1. I don't want to be too specific about what I mean by very close, so I'll just put it in inverted commas. And without making progress on this, we're stuck at showing that this thing that we're interested in is maybe bounded above by x divided by some large power of log x. Yep. Yeah, thanks. Is that better? And so this is somehow the best approximation we have, but this whole result is only non-trivial if Q is bounded above by some power of log x. So as I've stated it here, this has size maybe x over log x. So for this choice of constant 100, then this is non-trivial only for Q less than x to the power log x to the 99. And obviously 100 is not important here. You can replace 100 by 1,000, and then it'd be non-trivial for Q going up to log x to the power 999. But Q has to be of size logarithmic in x. And this is really a big issue for analytic number theory. It really limits lots of progress. And if this was all we knew, then there would be lots of different problems and applications which really remain out of reach. So one of the reasons that the Riemann hypothesis is viewed as the most important open problem in mathematics is because it points to some very fundamental deep structure within the prime numbers. But another reason why the Riemann hypothesis and the generalized Riemann hypothesis are viewed as some of the most fundamental problems in mathematics is because it would have lots of further applications to lots of other different problems. And so they're both fundamental and useful. Okay, let's try again a bit harder. Don't want to break anything. Okay, but that gets us to the Bombieri-Vinogradov theorem, which is maybe my favorite one of Bombieri's results. So it can take a few different forms, but maybe a weak version would be that the generalized Riemann hypothesis holds for most Qs. So this is equal to what you'd expect if the generalized Riemann hypothesis was true. Maybe with an error term that's ever so slightly bigger than what I had up there, but is essentially of the same size. So maybe I'll have log x to the power 100. And if this was true for all values of A and Q which are coprime, we'd have proven the generalized Riemann hypothesis, which would be great. But this is true for 100 minus little o 1% of values of q less than or equal to x to the half, maybe minus some fixed constant. So, okay, please continue to bug. So by this I mean as x gets larger and larger, we get closer and closer to 100% of different moduli q for which this generalized Riemann hypothesis statement holds. And so this is not proven the Riemann hypothesis, but it is proven that Riemann hypothesis for almost all values of q in this sort of statistical sense. And so at least if you're only looking at primes of a sensible size relative to q, then you can choose a value of q at random and be reasonably confident that the generalized Riemann hypothesis up to that sort of height will hold for your value of q of interest. So this is why it's often referred to as proof of the generalized Riemann hypothesis on average. And maybe a more typical statement, which is a little bit more technical, is that if you sum over all moduli q, which are a little bit less than x to 1/2, and you take a supremum over a and q, and then you look at this difference that we're interested in for the generalized Riemann hypothesis, you get an answer which is essentially the same sort of thing as what you get if the generalized Riemann hypothesis was true. So this is very interesting in and of itself as a result about the distribution of prime numbers in arithmetic progressions. But the key reason that I, at least personally, really like the Bombier-Vinogradov theorem is that, as was mentioned by Per, this is, for many applications, a perfectly adequate technical substitute for the generalized Riemann hypothesis itself. So one of the key reasons that we're interested in the generalized Riemann hypothesis is its profound other implications for the distribution of prime numbers, but the Bombier-Vinogradov theorem often allows you to deduce essentially the same consequences as you would do if you assumed the generalized Riemann hypothesis, now unconditionally. So you maybe have to work a tiny bit harder to incorporate this slightly more technical formulation, but otherwise it's basically as good as if the generalized Riemann hypothesis was true. So certainly when I have students who think about problems to do with the distribution of prime numbers, I'm always very happy to tell them to, first of all, make your life easy, assume the generalized Riemann hypothesis is true, and then once you have a result, assuming the generalized Riemann hypothesis, you can think about whether the generalized Riemann hypothesis is really necessary, and in almost all circumstances, either there's some big obstruction to do with Siegel zeros, in which case you've hit a famous roadblock, and it's likely that the theorem that you're trying to prove is kind of false if these putative Siegel zeros really existed, or you can use the Bombier-Vinogradov theorem and you can make your result unconditional. And so either there's this big famous obstruction, or you can make it unconditional using the Bombay-Vinogradov theorem. So this has happened for a number of different things. So I guess the Bombay-Vinogradov theorem came out around 1965, and I think lots of people were then going through different arguments to see in which ways this can make different results unconditional. So I certainly remember Peter Sarnak talking to me about when his student Zaharescu was working about Diophantine approximation with squares, and it went through exactly this process that Zaharescu had came up to Peter Sarnak and said very excitedly, "Oh, I think I proved this really nice result about Diophantine approximation with squares. I'm very pleased with it. The only downside is that I have to assume the generalized Riemann hypothesis." And Peter Sarnak said, "I wouldn't worry too much about that. You explain the result to me, and then I'll tell you how you can make it unconditional." And it was the ideas, at least behind the Bombay-Vinogradov theorem, that applied then. And maybe another famous example, or a famous problem at least, was how many ways can you express an integer as the sum of a prime and two squares? And in particular, can you write every large integer as the sum of a prime and two squares? So this was, it's maybe a slightly strange problem from today's perspective, but this goes back to Hardy and Littlewood. And they gave a conjectural answer. So they suggested that it should be possible to write every large integer as the sum of two squares and a prime, and they guessed a formula for how many ways you should be able to do this, or an approximate formula for when n is large. This was then proven by Hooley, assuming GRH. If I can spell. This was made unconditional by Linnik, slightly before the Bombay-Vinogradov theorem, but using a very technical argument that in some ways was a precursor to the ideas underlying the Bombay-Vinogradov theorem. But then, at least by modifying Hooley's argument, there's a very short unconditional proof. Using the Bombay-Vinogradov theorem. And so this old classical result from now 100 years ago started off being assumed by GRH, then was proven using very technical arguments, and now has a very simple, clean proof just using the Bombay-Vinogradov theorem as an application. But the story doesn't quite end there, because I guess recently there's a very nice paper of Assing, Blomer, and Lee, who have some technical extension of the Bombay-Vinogradov theorem that allows them to answer this question in a slightly more quantitative way. So Hardy and Littlewood said it should be approximately this number when n is large, and that's what all of these results were proving, that as n got very large, it was approximately Hardy and Littlewood's guess. But then there's a question as to how close to that guess really are you, and there was a natural sort of limitation in these sorts of arguments that meant that you could only get a fairly approximate answer using these sorts of techniques. But this work of Assenblum and Lee shows that actually this conjectural guess is rather more accurate than the previous works. So the point of this is that there are some of these sort of strange old historical questions going back to Hardy and Littlewood, and the whole question was initially solved assuming these big conjectures, was made unconditional. The Bombier-Vinogradov theorem was a kind of perfect drop-in substitute, but even nowadays, or just a few years ago, the Bombier-Vinogradov theorem is still very relevant and is still leading current developments. So that's supposed to just be a proof of concept that in various ways the Bombier-Vinogradov theorem acts as an unconditional substitute for these very powerful but out-of-reach results on primes and arithmetic progressions. Maybe I should use the spray. OK, great. So that's one reason that the Bombier-Vinogradov theorem is very powerful, that it sort of uses, it allows you to have a substitute for GRH. Another key reason is that this kind of quantitative result about primes in arithmetic progressions turns out to be an absolutely vital input to sieve methods. So sieve methods in general are it's a kind of collective noun for a number of different sort of techniques that apply in different contexts. But the way that I like to think of them is as tools that convert certain types of arithmetic information, maybe about a set or a problem, into other types of arithmetic information. So the picture that I like to have in my head is that sieve methods are a set of tools in analytic number theory, and you're interested in maybe trying to count primes or some other objects like primes in some set. So some set, I'll call the set A, and it takes in some arithmetic information about a set A, and it converts this arithmetic information into some other arithmetic information about the set A. So information about, let's say, the number of primes. So you take in some arithmetic information, and you use these sieve methods to convert that information into the information about the number of primes. And obviously, this is useful when this is the sort of information that you can prove, and this is the sort of information that you're interested in. And so, in particular, Enrico mentioned in his talk the question about gaps between primes. And so this is certainly something where sieve methods have been successful. And so in that context, The sort of arithmetic information that often you're interested in is the distribution of the set A in arithmetic progressions, and maybe some other sorts of things. And so for the question of small gaps between primes, at least after the work of Goldson, Pince, and Yildirim, the typical way of studying this was via sieve methods, and you take in as arithmetic information results about primes in arithmetic progressions. So exactly the sorts of results that the Bombier-Vinogradov theorem talks about, or the generalized dream hypothesis talks about. And sieve methods are these sort of combinatorial tools that allow you to convert information about primes in arithmetic progressions to results on small gaps between primes. The existence. And a key technical point is that somehow we know that this whole attempt at working like this would be completely useless if you were limited just to the ranges of Q that we're limited to by the z=0 effect, where Q is just of logarithmic size. But when you have something like the Bombier-Vinogradov theorem or the generalized dream hypothesis, when you can look at arithmetic progressions which are of size maybe roughly the square root of the size of the primes that you're looking at or something like that, then sieve methods can be rather effective at converting results about primes in arithmetic progressions into results on the existence of small gaps between primes. And so, as Per mentioned, one set of results that I've been quite actively involved in now sort of 10 years ago or so, but has been due to many different authors. So in no particular order, I'll put myself. There was the Polymath project. There was Tao. And there was Zhang. And maybe the whole setup in this way was at least partly due to Goldson, Pince, and Yildirim, although it certainly has lots of similarities to the much earlier work, including the work of Bombier and Davenport that Enrico mentioned earlier on. And so this says there are infinitely many pairs of primes P1 not equal to P2, so distinct primes, with P1 minus P2 different by at most 246. So the famous twin prime conjecture is the assertion that there's infinitely many pairs of distinct primes that differ by exactly 2. This is completely open, but as an approximation to that, you can look at pairs of primes which come very close together, and until the work of Zhang, we didn't know that there was infinitely many pairs of primes that differed by any finite quantity. And so, but we're now able to show that there's infinitely many pairs of primes that do have that do come unusually small close together, and we can't quite get down to 2, but 246 is some sort of quantitative approximation of 2. And at least, so Zhang's work, the key input to that was about trying to improve the arithmetic information that went into this sort of argument. And so the default arithmetic information that would go in would be the Bombier-Vinogradov theorem, and he had to prove a technical extension of the Bombier-Vinogradov theorem that allowed him to show that there's infinitely many pairs of primes that differ by some bounded amount. The later work of Tao and I refined the sieve methods at the heart of this argument, so it's more efficient at transferring this arithmetic information. And that meant that actually we didn't need Zhang's technical extensions of the Bombier-Vinogradov theorem, and so just the Bombier-Vinogradov theorem itself was the key unconditional input that we used to show this, combining it with sieve methods. And then the polymath project was about trying to quantitatively optimize things and get a smaller constant here as possible. 246 is the number that came out after various bits of numerical optimization. But again, this is highlighting very much how the Bombier-Vinogradov theorem is absolutely vital for the whole of sieve methods, that it's the kind of key input that goes into this whole field, and depending on the sieve method you're using, maybe you need a technical extension of the Bombier-Vinogradov theorem, or you can use a slightly more efficient sieve, then the Bombier-Vinogradov theorem itself can be the parallel thing. But even relatively recent advances in analytic number theory are still fundamentally relying on the Bombier-Vinogradov theorem as the key input. So maybe my first favorite result of Enrico is the Bombier-Vinogradov theorem, but my second favorite result that I thought I would also talk about here is a closely related result that's joint with Henrik Ivanic and John Friedlander, which goes beyond the Bombier-Vinogradov theorem and, in fact, goes beyond the reach of the generalized dream hypothesis. So in many ways, the generalized dream hypothesis can be seen as a sort of slight roadblock in analytic number theory, that that it's clearly an absolutely central conjecture, but we don't really have too many ideas about how to prove it, and so how can we make any progress beyond the generalized dream hypothesis if we are really stuck at proving it? But it turns out that at least in these maybe lo-fi versions of the generalized dream hypothesis for counting primes and arithmetic progressions, there's no terribly natural reason to be limited to the ranges that we were talking about before. So if you remember, I said that the generalized dream hypothesis was equivalent to the statement that the number of primes in arithmetic progressions has a very nice main term approximation of size roughly x to 1/2. Maybe I had a constant 100. But this is trivial in this formulation if q is bigger than the square root of x, because this error term here would then be bigger than the main term, and so this wouldn't even be an approximation then. But it's conjectured that despite the fact that this is well outside of the reach of the generalized dream hypothesis, that that this should, maybe I'll just write an approximately equals, that this sort of nice main term approximation should hold in a much wider range of q so again, I'm just going to write down some explicit constant here for the sake of being concrete. So if q goes up to x to the power 0.99, then this sort of approximation should still hold. It's clearly going to break down if q is bigger than x, and it breaks down in slightly technical ways if q is close to x. And so this is somehow well outside of the reach of the generalized stream hypothesis. Morally, it would imply that there's equidistribution of zeros on the half line between different L functions. But this seems way beyond anything that we're even tempted to speculate on at the moment. So it seems well out of reach of things, even if you start assuming pair correlation of families of L functions and the distribution of zeros on the half line, but nonetheless, we still expect this fairly natural conjecture to hold. And maybe one result due to Bombieri, Friedlander, Vaniec. I'll write them just as BFI because that's how everyone refers to these results. Says that you can get a version of the Bombieri-Vinogradov theorem that's unconditional, that goes beyond this Riemann hypothesis range of q being smaller than the square root of x. So let lambda q be a well-factorable weight which is some technical condition that I don't really want to get involved in too much. Then we have that if you look at all moduli going up to x to the power 4/7, you still get lots of cancellation, and so morally this is sort of saying that this conjecture holds in a slightly technical sense even when q goes up to the range x to the power 4/7. It holds on average. Sure. I'm trying to remember which pens I've used and which ones I haven't. Maybe I'll move to a blue pen and see if that's clearer. So this is sort of, oh, that looks much better. Beyond GRH on average. So the key point here is that 4/7 is bigger than 1/2. And it turns out for various results that this going beyond the square root barrier, so beyond the range of GRH, is crossing some important qualitative threshold, and there's certain applications to the distribution of primes and of other results of arithmetic significance which vitally rely on you going past this, just past this range of applicability of GRH. So as well as being a sort of a proof of concept that unconditionally we can do things that go beyond the immediate range of the Riemann hypothesis, this also has important arithmetic applications. And maybe I'll just highlight a couple of those now. So I guess one thing is that, as I mentioned, sieve methods, just as I'm raising here, often take results about primes in arithmetic progressions as a sort of black box arithmetic input. And so this is a technical result about primes in arithmetic progressions that goes beyond the Bombieri-Vinogradov theorem. And so just overnight, this automatically improves a whole load of different results about coming out of sieve methods, because you can put stronger arithmetic information into the sieve methods, and so you get stronger arithmetic information out. Because there's this slight technicality about well-factorable weights and things, you have to be careful about precisely which applications get improved and don't get improved, but there's a huge number of results in sieve methods that just get improved overnight as soon as you have this statement, and there's lots of places where the constant 1/2 can just be replaced by a constant 4/7. But maybe that just gives quantitative improvements, and so is an important psychological barrier that's been overcome, but less sort of fundamentally arithmetically significant. But two results that really rely on going beyond this square root barrier. So maybe one result, the first one that I'll mention, is a result of Fouvry and then independently Adelman and Keith Brown. Which says that Fermat's last theorem holds for infinitely many prime exponents. So obviously this isn't such an impressive result once you know Andrew Wiles's result that Fermat's last theorem holds for every exponent. But this predated Andrew Wiles's result by more than a decade, and the key technical information that went into this result of Adelman, Heath Brown, and Fuvey was a result on primes in arithmetic progressions, sort of morally of the shape of this BFI result. So there was quite a slightly different formulation, but it was these ideas about primes in arithmetic progressions to moduli beyond x1/2 and beyond this square root barrier that was the key arithmetic input, and at least at the time, that was maybe the strongest result in the direction of Fermat's last theorem by some metric. Maybe I've already mentioned the result of Yiteng Zhang from 2013, that there exists bounded gaps between primes and Zhang's result was very much inspired and followed much of the spirit of this result of Bombier, Friedlander, Vanic. Obviously, he had to come up with several impressive innovations on his own, but the key input for Zhang's result about bounded gaps between primes was not a result in sieve methods at all. It was all about a technical extension of the Bombier-Vinogradov theorem to moduli which was slightly bigger than the square root of x and slightly beyond the Riemann hypothesis range. And so just as so this result is kind of, for someone who likes primes and likes sieve methods and things, I find this a very pleasing result as both as a practical tool and also as a psychological tool that we can actually prove results that, from the point of view of sieve methods, the Bombier-Vinogradov theorem is as good as the generalized Riemann hypothesis, and there's very little to be gained if you assume the generalized Riemann hypothesis from the point of view of sieve methods only. But actually, with these sorts of results, you can actually go beyond the generalized Riemann hypothesis and you can prove stronger results. And so maybe I'll finish with just some very a recent project that I completed maybe last year, which was trying to improve upon these sorts of technical results about primes in arithmetic progressions marginally beyond x1/2. And so I have some slightly different technical condition, which I'm going to call triply well factorable. Then we can get a similar result, but now improving on the 4/7 to a 3/5. So again, if we're playing this quantitative game as to how far beyond the generalized Riemann hypothesis can you go, then in your dreams, if you believe this conjecture, you should be able to get a constant arbitrarily close to 1. The generalized Riemann hypothesis, or the Bombier-Vinogradov theorem, corresponds to 1/2. There's this proof of concept getting 4/7, and my result now gets us up to 3/5, which is the current world record. So I don't know if this means we're 20% beyond the generalized streaming hypothesis from the point of view of sieve methods, but hopefully this has given you some appreciation of how Bombier's work has been hugely influential in the development of prime number theory and sieve methods. His theorems still continue to have very important impacts, even in current research, and variations on his results are very much current topics of interest. So thanks a lot for listening. Maybe I'll pass over to questions, but I just want to say congrats, Enrique, for a very well-deserved prize. Thank you very much.